This is section 8.3, part A, estimating a population mean. So if we think back to Mr. Schill's call for the mystery mean activity, we found the value for that one sample to have a mean of 240.79 from a simple random sample of size 16. This task was to estimate the unknown population mean mu. They knew that the population distribution was normal and that its standard deviation was 20. Their estimate was based on the sample distribution of x bar. So again, remember to find your sample distribution. You're going to take the distribution or standard deviation for the entire population and divide it by the square root of the sample size. Or in this case, you're going to do 20 divided by the square root of 16, which is how they got 5 for their sampling distribution standard deviation. The figure above shows this normal sampling distribution once again. To calculate a 95% confidence interval for mu, we use our familiar formula of the statistic plus or minus the critical value times the standard deviation of that statistic. Because we are doing a 95% confidence interval, our z-star value would be 1.96. Remember to get this, we know that 95% of the data falls within the center, so that's going to leave us 5% for the two tails, or 2.5% on the left and 2.5% on the right. If we focus on this part to find this value right here, what our z value is here, this has an area of 0.025 to the left of that z value. So if we go to our z-score table, or table A, and we look up an area of 0.025, we're going to get a z value of negative 1.96. Our critical value is always the positive version of that. So our critical value, or z-star, for a 95% confidence interval will always be 1.96. That tells us that how many standardized units we need to go so the middle percent is 95%. Now, we know that our sample mean was 240.79 plus or minus our z-star value, which in this case our critical value is 1.96, times the standard deviation of the sample. Remember to find the standard deviation of the sample, you do the standard deviation of the population divided by the square root of the sample size. Or in this case, our interval will go from 230.99 to 250.59. We call such an interval a one sample z interval for a population mean. Whenever the conditions for interval, random, normal, and independent are satisfied and the population standard deviation is known, we can use this method to construct a confidence interval for mu. So, on a one sample z interval for a population mean, if you draw any simple random sample of size n from a population having a known mean and a known standard deviation, as long as it's normal and independent, then we can use this confidence interval C as shown, which is x bar plus or minus the z star times the standard deviation of the population divided by the square root of the sample size. The critical value z star is found from the standard normal distribution. This practice isn't very useful though, because in real world settings you usually don't know the population mean and you don't know the population standard deviation either. But we can use the one sample z interval for a population mean to estimate the sample size needed to achieve a specific margin of error. This process mimics what we just did in population proportion in section 8.2. So when you need to determine how to choose a sample size for a desired margin of error, you need to get a reasonable value for the population standard deviation from earlier or pilot studies. You need to find the critical value z star from the standard normal curve, and you need to set the expressed for the margin of error to be less than or equal to whatever you're looking for. So for our margin of error formula, we can say z star times the standard deviation of the population divided by the square root of the sample size must be less than or equal to your margin of error. So researchers would like to estimate the mean cholesterol level, mu, of a particular variety of monkeys that are often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. A previous study involving their variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. Obtaining monkeys is time-consuming and expensive. So the researcher wants to know the minimum number of monkeys that would be needed to generate a satisfactory estimate. So we know that our formula is Z star times the standard deviation over the square root of n is less than or equal to the margin of error. Since we're doing a 95% confidence interval, our Z star value is still 1.96. And they tell you in a previous study that they assume that the standard deviation is 5%. So we can go ahead and use that previous information into this problem. And we're going to divide that by the square root of n, and we want our margin of error to be less than or equal to 1 deciliter per milliliter. So if we want to get the n by itself, we can multiply both sides by radical n. If that number was anything besides 1, we could also divide both sides by 1, or whatever that value is for your margin of error. We could then square both sides to get the n value by itself, and we would see that n needs to be at least 96.04, but we can't have part of a monkey, so we would go ahead and tell them to round up and tell them they would need at least 97 monkeys to estimate the cholesterol level to their satisfaction. Here's a caution. Notice that it is the size of the sample determines the margin of error. The size of the population does not influence the sample size we need. This is true as long as the population is much larger than your sample. So let's check our understanding. To assess the accuracy of a laboratory scale, a standard weight known to weigh 10 grams is weighed repeatedly. The scale readings are normally distributed, but with an unknown mean. This mean is 10 grams if the scale has no bias. In previous studies, the standard deviation of the scale readings has been about 0.0002 grams. How many measurements would be averaged to get a margin of error of 0.0001 with a 98% confidence interval? Show your work. So we would first need to start by finding our critical value, or our Z star. If we have a 98% confidence interval, that means we're going to have 2% left for the tails, or 1% left on each side. So this is going to give us an area of 0.01. So if we look up that area of 0.01 on table A, or our Z table, we're going to find that this Z value would be negative 2.33, or that our Z star value will be a positive 2.33. Now we know that our formula is Z star times the standard deviation over the square root of n is less than or equal to the margin of error. We know from a previous study that our best guess for a standard deviation is 0.0002, and we know that our margin of error needs to be 0.0001 or less. So if we fill in this information, we can multiply both sides again by that square root of n, and then we can divide both sides by that 0.001 to get the square root of n by itself. You can go ahead and do all of these calculations on the left to get 4.66, which is less than or equal to the square root of n. And to get the n by itself, you can then square both sides. And we know that our sample size needs to be at least 21.71. Now you can't have part of a measurement, so that needs to do at least 22 measurements to get a margin of error of 0.0001 with a 98% confidence interval.